Okay, class. So I'm sitting here on a Friday night and I've decided to go ahead and do a video of the proof that the product rule is the product rule using the limit definition, which is something I said we didn't have time for in class. And I don't think I've ever made a video about this before. I know I've done it in class before, but not a separate video. So why not, right? It's a good way to unwind on a Friday night. So a couple of things first. This is more of a kind of a big picture idea here. So in math, there's something that we've been doing for a long time that has been very helpful. All right. So like when you have, let's say 2 over x plus, I don't know, 5 over x plus 2. If you had to combine those two together, get a common denominator, then what you do is you multiply this one by x plus 2 on top, x plus 2 on the bottom. Then over here, you multiply by x over x. This step right here, all we're doing here, by doing this, we're just multiplying by 1. So we're using this, and same thing over here, we're multiplying by 1. So this is something that we do a lot, right? Anytime we have something algebraically, we've always well, not always, but sometimes, right? We find it necessary to multiply by 1. And then we just get real clever on how we rewrite that 1. And it becomes very helpful, right? It allows us to progress through the problem. So that is a pretty advanced idea. If you just think back to just what it really is, right? You're taking some arbitrary expression, multiplying it by 1, and then just being very creative in how you're using that 1. That's pretty good. But there's also another thing that we do in math that is similar to this, but is actually a more advanced idea. And that is this idea that if you have any expression, no matter what it is, let's say x plus 5, that you can always not multiply by 1, you can always add nothing to it, right? So I can always add nothing here, and it doesn't change the problem. Just like multiplying by 1 doesn't change this expression, right? It just makes it look different. Adding 0 does the same thing, right? You take something, add nothing, same thing. Now, the way I write that 0 is totally up to me. I could take that 0, I could make it a minus 3 plus 3. And it would still give you the same answer, right? At the end of the day, that would still be just x plus 5. If I wanted to, I could do minus 3x plus 3x. It's still going to be x plus 5. I could do plus 3x minus 3x, right? It doesn't even matter which one I do plus, which one I do minus. Just if that part in blue turns out to wipe each other out and it's just nothing, then we're not changing the problem, right? It just looks different. This is a very advanced idea. Call this a hidden 0, right? This is a hidden 0. And it's used a lot in mathematical proofs. This right here was a hidden 1, which we do a lot, a hidden 1. So with that in mind, let's talk about how it is that we can prove the product rule. So the product rule, the way I presented it to you in class, is that if you have some function f and you multiply by g, and you want to take the derivative, then it's going to be f prime times g plus g prime times f. Okay, so that's what I presented to you. I told you that the book does it a little different. They changed the order, but at the end of the day, it's the same formula that I present to you. So I want to prove to you that that's true, and I want to use the limit definition to do it. So here's first what we need to get in order. When we were talking about the derivative of a function, let's say we take a function f, and we say, what is its derivative? The definition, okay, this is the definition of what the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h, okay? That is the definition of the derivative. So if I ever see this limit sitting somewhere, it means f prime of x, right? That's what it means. And sometimes when we, sometimes when we define something in math, we'll put a colon in front of the equal sign, and that's letting you know we're not saying the left side's equal to the right side. We're saying this expression is defined to be this. Okay, and that's what this means. This notation is actually this limit. All right. Now, similarly, if we wanted to know the derivative of g, right, the only thing that changes in the problem, or the only thing that changes on the right-hand side, is the function. So instead of f of x plus h, it becomes g of x plus h, and then minus g of x, and then all over h. Okay, so that's the definition of g prime. And it doesn't matter what function this is. If I want to know m prime of x, right, this would be the limit as h goes to 0 of capital M of x plus h minus capital M of x all over h. I hope you get the idea. Okay, main idea is whatever function is here, right, that is what goes here, 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 right? Okay, so now I'm going to try and prove this, but to prove it, I'm going to just use some slightly different notation. What I haven't read here is like the really, really short way of writing the product rule. The more precise way would be to say, okay, you've got some function of x times some other function of x, f and g, and you want to take their derivative. Okay, the derivative should be the derivative of f times g of x times plus the derivative of g of x times f of x. Okay, so that's really the product rule written out, more using more, I guess, precise notation. So this is what I need to try and prove to you, all right? I've given this to you, you've taken it on faith, but I'm going to try and prove this. So the way I'm going to prove it is I'm going to start with the left-hand side. Okay, I'm going to start here. And then I'm going to start working it out. And hopefully at the end, when I'm done working this out, you'll agree with every step I do. And at the very end, it's going to look like the right-hand side. And then I will have proven that these are equal. All right, so let's start with something. Let me first define. I'm going to define right now capital M of x to be equal. So I have some new function that I'm coming up with called capital M. I'm just making it up right now. And what it is it's actually just the f function times the g function. That's all it is. So you give me two functions, f and g, and I have this new function, capital M, which is just their product, right? So if I said, hey, what's m of 2? You just plug 2 into both of these. If I say, what's m of 5? You plug 5 into both of these, right? So now let me talk about this right here. What is this? Okay, so the derivative, if you take f of x and you multiply times g of x, right? What is its derivative? Well, this f times g, I just define that to be capital M. So this really means take capital M, right, and take its derivative. Another way you could write that is what's m prime of x? Well, we just said over here that m prime of x would just be this. It would be capital M with x plus h plugged in, minus capital M with x plugged in, and then divide by h. That is the definition of the derivative of capital M. But, so I should say that this equals this, which equals that, which so far equals this, right? Now, again, what does it mean to take m and plug x plus h in? That means you're going to take x plus h, plug it in here, plug it in here, plug it in here. So watch. This becomes, okay, this part becomes f of x plus h. Oh, I forgot the limit out here. Oh my goodness. Limit h goes to 0. My goodness. All right. Maybe I've chosen to do this too late in the night, but go for it. Okay, so we have the limit now. To plug x plus h into m means to plug it in here and here. So that really means take f, plug x plus h in, multiply that times g with x plus h in. That's this top left, minus now m of x itself, which is just this original function, which is f of x times g of x. And then all of this over h. So again, this product, take the derivative, is equal to figuring out what this limit is right here. So now I'm going to have some fun. So let's take that limit. What I'm going to do is I'm going to realize that there's a hidden 0 here. Okay, so the hidden 0 is this. Let me paste it here again. All right, right here. Slide this guy down a little bit. Okay, minus g of x right there. Okay, right here, there is a 0 right there. right after this product, there's a plus 0 and then minus this. So I haven't changed anything, just like earlier, right? If we add nothing, right, doesn't do anything. But the way I'm now going to rewrite this is going to be extremely clever. And I'm not taking any credit for this cleverness, okay? This is something somebody else figured out, and it's just taught. And then eventually you start to realize, if you're a math major, that you have to start figuring out what these hidden zeros are on your own, which becomes much harder. But that's not for here, okay? All I'm here to show you is that this hidden zero can be rewritten in a very clever way. Here it comes. So I'm going to now rewrite that 0. And I'm going to need to slide this down a little bit further for this hidden 0. Okay, here it comes. How should I rewrite that hidden 0 so that this is all going to work out? So I'm going to write it as minus f of x times g of x plus h. I'm going to need a little more room. So I'm subtracting some weird expression there that I've just come up with on my own. And then plus f of x times g of x plus h. Whoa, what? Right? Like, how would you ever come up with that? That is weird, right? But just watch what happens. All right, so we have all of this stuff on top of h, right? Here's h down here. So realize that we have 1, 2, 3, there's 4 terms. So I could just use algebra and break this into 4 different fractions, each one of them over h. But instead of doing all 4, I'm just going to split it down the middle, and I'm going to do the first 2 over h and then the second 2 over h. Okay, let's do that. Limit h goes to 0. Okay, the first 2, f of x plus h times g of x plus h, then minus this right here, right, which is going to be f of x times g of x plus h, both of those terms over h. And since I'm splitting it up into 2, I'll just do plus and now a new limit. It's still h goes to 0. And now it's the second 2 terms, f of x times g of x plus h minus the f of x times g of x all over h. All right, we're getting there. Now, the next step is to realize that in this first limit, we have a common factor. They both have a g of x plus h. And so watch what I'm going to do. This is just purely algebra here. Since they both have those, I can factor it out, and I can place it out in front. So watch, I'm going to put it as g of x plus h out in front of whatever was left on top, which is f of x plus h minus f of x, and then over h. Now, just double check this. What I'm saying is, since these both have a g of x plus h, I can pull it out, which is here. If you were to multiply this back through, because this is times a fraction and there's 2 terms here, you would have to distribute that g of x plus h through both of those, and then you get back this. So this is completely legitimate for me to write this way. And then on the other one, notice that I have in common an f of x, okay? So that means this turns into the limit. H goes to 0. Let me pull that f of x out. And then I have g of x plus h is still there, minus g of x, and then all over the h. Okay, same story. If I multiply this back through, I get back this. Now, because I'm taking the limit and I have a product, I can do the limit of each one individually. That's a major plus with the, when you're talking about limits, there's no restriction. You just pass the limit through everything. So let me show you what I mean here. I'm going to have to move some stuff. It's nice I get to cheat here. So I'm going to move this down. So X, what I'm going to do is I'm going to take this, move it down a little bit, take this, move it down a little bit like this. So what I'm doing is, since I'm doing the limit of this product, I'm going to do the limit of each one. And then the limit of this product, I do the limit of the first one times the limit of the second one. All right, let's let h go to 0. Okay, so if h goes to 0 on this first expression, this little guy goes away, and all you're left with is g of x times. Now here, well, wait a minute. Here, wait a minute. What is that? That look familiar? Does that look familiar? What is this? Well, that is the definition of f prime of x. Exactly. So that is f prime of x right there. That's what that is. And then I have plus, and then over here, if I let h go to 0 on this, well, there is no h there, right? H has no impact on this expression because there are no h's in it. So that just stays f of x. And then times, and then again, this is the definition of g prime right there. And so that becomes g prime of x. And now if we just, well, because multiplication is commutative, I'm just going to switch the order of these and switch the order of those. And if I do that, I think you see it already. You probably saw it a few steps ago. It's going to be f prime of x times g of x plus g prime of x times f of x, which the way I wrote it in class is f prime times g plus g prime times f. And therefore, you have the proof, right? That's pretty cool. You start out with you start out with the left-hand side, right? I define this function m, which is just their product. And the only reason I did that is just to kind of help you see why when you plug x plus h into m, you get this. But if you can follow this, really the only real kind of crazy step is this 0. Once you have this 0 and you rewrite it the right way, this has to be perfect for this to work. Then everything just kind of flows and then you get your product rule. Pretty cool. Anyway, that's the proof. I'm contemplating whether or not I should do the proof for the quotient rule. We'll see. I'm going to post this and then see if I get some feedback that you want to see the quotient rule. Then I'll put together a video. Anyway, have a good one.